Hello, it's me, Maria Sandoval, and today I will be presenting on thermochemistry, and we're going to be starting with writing formation equations. So our problem is write a balanced equation for the formation of 1 mole of the following compounds from their elements in their standard states, and include DH to the degree of F. So we have A. Silver chloride, AgCl, a solid at standard conditions. B. Calcium carbonate, CaCO3, a solid at standard conditions. C. Hydrogen cyanide, HCN, a gas at standard conditions. So those are our three I guess your compounds, yes, the compounds that we are working with today. So our plan is to write the elements as reactants and 1 mole of the compound as the product formed. Make sure all substances are in their standard states. Balance the equations and find the value of DHF in the table 6.3. So our solution for our AgCl is Ag solid plus 1/2 of chloride Cl2 gas. So usually if you see this, anything with a 2 is usually a gas. So you see you have O2 gas, N2 gas, H2 gas, but that's like just usually that number. So we have our 1/2 of chloride gas. This gives us AgCl solid, and that's what our compound is. So we're basically finding what builds our compound, and that means that our DH of F equals negative 127.0 kilojoules. For B, for our calcium carbonate, we have our calcium and our carbon. Calcium solid, carbon graphite, which is solid, plus 3/2 oxygen gas. And there again is our 2 for the gas. Sorry, I'm not feeling that well. A little bit of a bug. This gives us our products CaCO3, a solid, and this equals negative 1,269 kilojoules. For C, we have hydrogen cyanide, HCN, which is a gas at standard conditions. This is 1/2 of hydrogen gas, H2G, plus C, graphite, plus 1/2 of N2G, which is our gas again. This gives us HCNG, which is a gas, and this is our hydrogen cyanide. This is 135 kilojoules. And so we're moving on. Sorry about that. Someone came in and I wasn't sure if they would be interrupting our presentation. So, moving on, we're talking about the natural greenhouse effect, so the trapping of heat by the atmosphere and chemical connections. So here's the natural greenhouse effect, and on the other side is the enhanced greenhouse effect. So here we're showing that IR radiation is trapped by the atmosphere, and the IR radiation heat is emitted by the Earth at the same time. Light is absorbed by the surface and is converted into heat, and at the same time some of it is being reflected by the surface and also being reflected by the atmosphere. So a portion of it is being taken in and a portion of it is being reflected for our heat and our radiation. For our light and our radiation, the light is converted into heat. In the enhanced greenhouse effect, you see that there's way more carbon dioxide over here. So more CO2 in the atmosphere traps more heat, and more heat in the atmosphere warms the surface further. And you can see that some of it is reflected and some of it is also being emitted by the Earth, but we're still taking in more. So our carbon dioxide is at 60%, our CFC is at 8%, the ozone is 12%, nitrous oxide is at 5%, and methane is at 15%. Moving on, we're talking about evidence for what we just saw, the enhanced greenhouse effect. So since the mid-19th century, atmospheric CO2 has increased. And here you can see we're starting from the 19th century, from 1860 to 2040, and we have our CO2 concentration, which is parts per million, and we go from 200 to 500. And as you can see, starting all the way back in the 1860s, we're seeing a gradual increase, and we can only predict it to go up farther, which is why we're saying that the atmospheric CO2 has only increased. And since the mid-19th century, average global temperature has risen since 0.6 degrees Celsius. Here we have our timeline again from 1860 to 2040, but here on the right side we have our temperature change now in degrees Celsius. I'm going up by 0.5 increments, so negative 1.0 all the way up to positive 4.0. So the trend here shows that we have a line only going up. So our global temperature is only rising, as is our CO2. So here I'm going to be talking about the specific heat capacities of some elements, compounds, and materials. So it's 3 different sections. So first we're going to be talking about our elements. And so we have our substance here and our specific heat here. Don't get confused because this is a completely different chart. Or not different chart, but different objects. So we're ignoring that half of the page and we're only looking at this one. So for our elements, for aluminum, the abbreviation is Al. Our specific heat capacity is 0.900. For graphite, it is 0.711, iron 0.450, copper 0.387, and gold 0.129. Moving on to our solid materials, we're starting with wood. It's 1.76. Your cement is 0.88. The glass is 0.84. The granite is 0.79, and steel is 0.45. And once again, these numbers are a specific heat capacity for that substance. Moving on to our compounds, water, H2O, is a liquid. The specific heat capacity for that is 4.184. Ethanol alcohol, C2H5OH, the liquid, is 2.46. Ethanol glycol, CH2OH2, is a liquid, 2.42, and carbon tetrachloride, CCl4, liquid, is 0.862. And once again, those numbers are our specific heat capacity, and the compounds are here. I think that is the end of our presentation today. Thank you so much for listening, and I'm sorry for sniffling and rubbing my nose a lot during this. I think I may have caught a little bug. So thank you for your patience, and I'll see you all in the next video. I hope you learned a lot because I sure did too. Bye.